Hello everyone, I am Ronak Patel. So in this video we will see what is activation function. This is structure of artificial neural network. So the inputs to this neuron is your feature x1, x2, x3. This first part of your artificial neural network will sum it, and then the next part will perform some activation on that sum. That is your output. So this is a artificial neural structure. And as I said, that is divided in two parts, sum and your activation. There are different activation functions in neural network. So this is the simple architecture of artificial neural network, that is one neuron, or we can also say it's a perceptron. So same perceptron we have shown in this computation graph. So you can see this, the inputs are X, W and B. W and B are weight and bias. There will be some random initialization of it, W and B. Then Z is calculation of W transpose X plus B, and then activation on that. G is your activation function. And then we'll find out the loss between actual and predicted. This is for perceptron. This is multi-layer neural network architecture. This is two-layer architecture. As you know that we don't count input layer when we count layers of neural network. So this is the weights to layer 1. These are the weights to layer 2. So if I need to indicate these weights, then I can indicate like this W1, and this is W2. Right? We'll see next the computation graph of this multi-layer neural network as well. So this is the computation graph of this multi-layer neural network. So this each layer and the neuron in that particular layer, that is divided in two parts, sum and activation. So for this layer, each neuron sum and activation, for this neuron sum and activation. So this portion, this is for layer 1, and this is the vectorized version. So at one shot you can calculate your Z for this layer and your activation on that Z for layer 1. And this is your second layer. This is also vectorized version. So again you can calculate Z and activation on that Z, and you can predict. So this is the computation graph. Now here your G, and in second layer G, this is your activation function. As I said, there are different activation functions. You can use different activation function for particular layer. So if I want to use some another activation function for layer 1, then yes, I can use that G1. And if I want to use some another activation function on second layer, then I can use that as well. Right? Okay. What is activation function in neural network? The purpose of the activation function is to introduce non-linearity into the output of neuron. Why activation functions? A neural network without an activation function is essentially just a linear regression model if you don't add non-linearity in that. The activation function does the nonlinear transformation to the input, making it capable to learn and perform more complex tasks. That's why we require activation functions, right? Okay. So in the previous example, as you see that we have calculated the Z1 and then some activation on Z1. If we remove that activation, then to next layer, the input is Z directly, right? So if you see that part, then let's write over here. So your A1, that is activation on Z1. If you don't apply activation, then this part will be removed and your A1, that is equal to Z1. When you calculate Z2, Z2, your Z2 is W2 A1 plus B2. This is your Z2. Now if you replace A1 with Z1, and what is Z1? Z1 is, if you replace A1 with Z1, and Z1 is W1, your feature X plus bias to layer 1. This is your Z1, and as A1 is equal to Z1, so I can directly write this. So W2 into this plus your bias B2. If you solve this, then ultimately what you will get the equation like this: W dash X plus some your bias dash, means W2 W1 into X plus your bias, that is B1 B2. So what is this? This is your linear function only. If you don't add activation in this, right? So that's why we require activation function. Okay, so first activation function, that is linear function. So it's a linear function, has the equation similar to as of straight line, that is y is equal to ax. So you know the equation, that is y is equal to mx plus c. So if we don't count constant, then that is y is equal to ax. No matter how many layers we have, if all layers that are linear in nature, the final activation function of last layer is nothing but just a linear function, which I have shown you in the previous slide. If output has sigmoid and all other linear activation, then it is just a logistic regression. So as we have seen in the perceptron, the sum part and your activation part, and in activation we have used the sigmoid, then that perceptron, that is a logistic regression. Now the same way in multi-layer neural network, if we use linear activation in all other layers and sigmoid at the output layer, then that will become a logistic regression only, right? Now in the case of the linear regression, the linear function is used at the output layer. Linear function that is used at the output layer. But hidden layer must have some non-linearity. Means there must be some activation function in the hidden layer. Then that model will work as a linear regression. So the problem with this linear function is it missing non-linearity if you use just a linear function. Next is sigmoid activation function, right? For logistic regression, we have used this sigmoid activation function. So it's it plotted as a S-shaped graph, which you can see over here. The equation is f of x is equal to 1 over 1 plus e raised to minus x. So if you plot this, then you will get this graph, right? So at 0, you can see the value is 0.5 is the value. Now the value for this graph, that is ranges from 0, you can see it ranges from 0 to 1. What is the uses of this sigmoid activation function? It usually used in output layer of a binary classification where result is either 0 or 1, right? As value for sigmoid function lies between 0 and 1. So result can be predicted easily to be 1 if value is greater than 0.5 or 0 if value is less than 0.5. At the output layer, if we use this sigmoid activation function and we get the value 0.6, so we can classify into class 1. If the value we get that is 0.2, then that is a class 0, right? So you can classify it, means for binary classification this sigmoid activation function is useful. Now what is the problem in this sigmoid activation function when you use this sigmoid activation function? So the problem with this sigmoid activation function when used in hidden layers, that is a vanishing gradient problem. So we understand what is that vanishing gradient problem, right? So when the value become very small or very large, right? When it's very large, the value that you will get or slope that you will get is 0. When it is very small, you can see here the sigmoid activation function will give you value 0, but here the slope that is also 0. So your learning algorithm that depends on derivative. What is derivative? Derivative is a slope only. So here also when value is large, you will get slope like 0. Here also when values are small, the slope is also 0. So what this indicates? It indicates that there is not much learning that is going on now, right? So this is a vanishing gradient, means learning is not happening now or very less learning is there. So this problem is there in sigmoid activation function. But this is useful activation function at the output layer, right? But we need to avoid to use this in a hidden layers. Next is hyperbolic tangent activation function or Tanh we can say. And this is actually a mathematical shifted version of the sigmoid function, right? So you can see here instead of that 0.5, now the value is 0 over here for 10h. So you can see it's the same as, but now it's shifted to 0 rather than 0.5. The equation is e raised to x minus e raised to minus x upon e raised to x plus e raised to minus x. Or if you want to write in terms of sigmoid activation function, then you can write 2 multiplied by sigmoid 2x minus 1. The range of sigmoid activation is from 0 to 1. The range of this tanh is minus 1 to 1. What is the uses of this tanh? This is usually used in hidden layers of a neural network as its value lies between minus 1 to 1. Hence, the mean for the hidden layer comes out to be 0 or very close to it. Hence, this will help in centering the data by bringing this mean close to 0. So, it centering your data to some or scaling your data. This makes learning for the next layer much easier, right? That's why you should use this tanh in hidden layer. But again, it's the same shape that we have seen in the sigmoid. So same that vanishing gradient problem. will arise in this 10H as well. So you can see here the slope is 0. Here also slope is 0. So that vanishing gradient problem will be there. Now next and most popular activation function, that is ReLU, Rectified Linear Unit Activation Function, and it is most widely used activation function and implemented in hidden layers of neural network. The equation of that is f of x is equal to max of 0 comma x, means whenever you have a value, negative value, the output is 0, and if you have some positive value, then output will be that positive value. So the range of this activation function, that is 0 to infinite, no negative value. So same thing you can see in this graph as well. When there is a negative value, at that time the output of this activation function is 0. When it's positive, then you can see the output is that positive value, right? Okay. Now uses of ReLU is less computationally expensive than Tanh and Sigmoid because it involves simpler mathematical operation, max 0 comma x, which is a simpler. So at a time only a few neurons are activated, making the network sparse and making it efficient and easy for computation. Because if some values are negative, it directly makes it 0, and for other value, positive value, it activates that neuron, right? So that's why it makes this neural less complex. Now, what is the problem in this ReLU activation function? That is a dying ReLU. Means some neurons are dying since the output is 0 for all negative values from that neuron. It causes some nodes to completely die and not learn anything, because due to that negative value we get it 0, right? So, and this thing sometimes helpful as well, as we want to omit some of the neurons, but yes, there is a problem, there is a dying ReLU. To solve this, we have a leaky ReLU activation function. So instead of making this negative value 0, we multiply it with some value alpha, right? So alpha is your hyperparameter, generally set to 0.01 for leaky ReLU. If you take any other value of alpha, then that is a parameterized ReLU. Leaky ReLU solves the dying ReLU problem to some extent. Now you can see here for negative value, it is not directly 0, but there is some slope over here, right? In previous one, it is just a horizontal line, so there is no slope and no learning. So if we set alpha is 1 here, then your liquid will become a linear function, that is f of x is equal to x. Directly it will take the value of x and will be no use, right? So this is your leaky ReLU activation function. Next is a softmax activation function, is more generalized from the sigmoid, and it is used in multi-class classification problems. The equation is like this: s of xi is equal to exi upon sigma j is equal to 1 to n, means the neurons in that layer, exj means summation of all the output. It uses to use softmax, usually used when trying to handle multiple classes, right? So the softmax function would squeeze the output for each class between 0 and 1. We have seen the sigmoid activation function that is used for binary classification to classify in 0 or 1. So value greater than 0.5, that is we can classify as 1. If less than 0.5, we classify as 0. If you have multiple class, right? So in multiple class, suppose dog, cat, lion, like this, and you want to classify in this multiple class, then when you use sigmoid activation function, it will give you a different probability like 0.6, then 0.4, and then 0.7, like this. Now if you add this, then you will not get 1. But the rule of probability is the summation of all probability should be 1, right? So that problem will be solved by this softmax activation function. So what it does, it will take the output from all the layers, it will add it, and your output from that particular neuron in the output layer. So if we divide that by your summation from all the output layer, then you will get some value. Same way for all the output layer, if you get this value and if you add it, then the probability sum will be 1, right? And that thing we want, means out of these three class, we want that the value should be 1 for only one class. So whatever the probability, or for whichever the class the probability high, we will tell that this feature belong to that particular class, right? So that is softmax activation function. So this is also used at output layer and when we have multi-class classification. Now very important, choosing the right activation function. So Sigmoid and Tanh has a vanishing gradient problem. So try to avoid that activation function. If your output is binary classification, then sigmoid function is very natural choice for output layer only, right? For binary classification, both sigmoid as well as softmax are equally approachable. But in multi-class classification problem, we generally use softmax and cross entropy along with it. So for multi-class classification, you should go with softmax. Or for binary classification as well, you can use softmax as well. Basic rule of thumb is if you really don't know what the activation function to use, then simply use ReLU in your hidden layer as its generally activation function and is used in most of the cases. Again, you can use different activation function in different layer as well. Suppose I have 3 layers, 2 hidden layers and 1 output layer. So in hidden layer 1, I can use ReLU activation function. In hidden layer 2, I can use Leaky ReLU activation function. And the output layer, that is layer 3. At that, if it's a multi-class classification, then I can use softmax activation function, right? So this way you can use different activation function at layer wise as well, right? So in this we have seen linear activation function, no use of it, and sigmoid, Tanh activation function, ReLU, Leaky ReLU, and softmax activation function. So that we have seen, right? In next video, we will see the derivative of different activation function. Thank you.